Okay. Working? Yeah. I start where we stopped last time. I claim the following theorem, and I will prove it now. The linear operator defined on the sample functions which gives to all sample function the Lebesgue-Schiltz integral, which is, we saw, a martingale. With bounded variation. So this was defined as a Lebesgue-Schiltz integral, right? This is an isometry. That is that the norm now in the L2 space, I consider this to be a subset of the L2 space. So the norm in the L2 space which was given by the constant d, which was the variance of the Levy process, and then is the integral, the norm squared is d times the integral of the expectation of the second moment. Well, the integral of the second moment of h. This norm here is equal to the norm here of this stochastic integral. Which is the second moment of this integral here. So this is what we want to prove. This was what we denoted by this norm. We denoted it in this way. It's the norm of on the space of martingales which bound second moment. So this is what we want to prove. This isometry. Okay. Proof. For the proof, we need only to use everything we saw in the previous lectures. So it's not difficult. So given a sample function, for example, like this. So if it is a sample function, then we know that, for example, Hg is E is adapted to the sigma algebra at time t. Then we just compute the norm in L2 of in this martingale space of martingales with a bounded second moment. So this is the second moment of the integral. So last time I didn't write it correctly. It was somebody who let me notice this, because here, in order to write it correctly, I should put that te plus 1 is not bigger than tau, t, than this t here. So minus L te intersection with. So this is the minimum of this t and t. Okay. Yeah, in this case, it's not necessary if I take TE less than T, but I wanted now to notice people that they should correct last time what was written, right? In this case, I take anyway T is smaller than T. Okay. So, okay, we just computed. It's an exercise. So, obviously, we have a mixed term, but also term where this appears twice. So, the term where the term appears twice are like this, is HE to the square. And then, so my Levy process is real valued, so I can write it like this. Okay, I agreed to skip now this. It makes me easier to write everything. So this is one term, but then I have the mixed term. And the mixed term looks like this. It is the expectation of the sum of all E from 1 to n, but then I have J bigger than E from 1 to n. And then here I have a scalar product. Yes, I am doing in Hilbert space. That's good. Okay, yeah. I have a scalar product. So this is LTJ plus 1 minus LTJ. Scalar product with HE. LTE minus plus 1 minus LTE. Okay, and now you can imagine we want to get rid of the scalar product because here we have done. Yeah, we will see this immediately. In some sense, here we are, this term here is already this integral here. And this we should show that it is equal to 0. Okay, so in fact, the first term is equal to the expectation. Okay, the expectation I can put it inside, so it's the sum of 1 to n E of the expectation of the norm of HE to the square. Now, HE was in the sigma algebra generated at time TE, so it is independent by assumption that this is a Levy process. So this is equal to the LTE plus 1 minus E LTE square. Then you see immediately that this is just, we use then stationarity and the fact that we know that the variance increases linearly with time, and we have done. But anyway, let us look at the second term. So the second term, now you see why my life here is easy. I mean, I took, as you told you, I am integrating Hilbert values functions with respect to Levy processes with values in R. Obviously, there is also a theory where this is maybe Hilbert valued, but I'm not doing this theory here. So for this theory, you might, I think, ask Rosinski or Wojcinski, but I think also Brezhniak, who will be here next time. But you see here that things are very easy because my Levy process is real valued. Because in this case, I can shift this term outside of the scalar product. So I multiplicate it outside. And then I look at this bracket, which remains in this way. It's HJ, scalar product with HE, LTE plus 1 minus LTE. Okay. And now let me do the next step. The first term, I use the stationarity of the Levy process. So as I use the stationarity, the first term will become simply the expectation of LTE plus 1 minus LTE squared. And then the next term, I use the fact that HE and LTE plus 1 are stochastically independent of the Levy process at time Tj and Tj plus 1, and stochastically independent I am sorry. Yes. So this is stochastically independent of this because this is in the sigma algebra at time Tj. And obviously this is also independent of this because the sigma, the time Te is a smaller time than this time here. So this is independent of the scalar product here. So this, I can write it as, this is a double sum with j bigger than E. And here I have the expectation of LTJ plus 1 minus LTJ. And due to the independence, I have that they are uncorrelated, and hence I get here Hj and He and LTE plus 1 minus LTE. But now we have done, for the second term, we see immediately that it is 0 because we assumed our Levy process to be centered. So this expectation is in any case 0. And the only thing which remains is the second term, which now we use the fact that we prove that the variance is linearly increasing. So this is then D times T. The second moment is linearly increasing, plus 0. Okay, but this here is exactly. Yeah. Thanks a lot. Yeah. Otherwise, the next step would be wrong. And this now is nothing else than the integral from 0t of the expectation of Hs, of the second moment of Hs in ds times d. That is, it is exactly the norm here. Maybe we denoted it in this way. So it's this norm here. Okay, so we have proven that this is an isometry between this space and this space for our sample function. Okay, but now you can imagine that we have done. Because we know that the sample function are dense in L2, and therefore, due to this isometry, we can prolongate our operator Ito integral on the whole L2 space by approximation through the sample functions. And what we get is a linear continuous operator, and this linear continuous operator is exactly what we call the Ito integral. So finally, we were able to define this pathwise for the sample function, but we know we are not able to do it pathwise for all L2 functions, because eventually the Levy process might have a variation which is unbounded. But we are able to close this operator in L2. So this is what, what is in fact always very well known for Brownian motion. And you see that it is identically, without any difference, valid also for Levy processes. I will write, obviously, now the theorem on the blackboard. So the theorem says now, and you have seen that for Brownian case, the linear operator E, which we defined on the sample function with values in MT on the space of squared integrable martingale, and which gives to every sample function first as a value the Lebesgue-Schiltis integral, is closable to a continuous operator on the whole L2 space of adapted functions, again with values in the space of square integrable martingales. Okay, the proof is now really one line or two. Moreover, this operator is an isometry. Okay, the proof is obvious because it is clear that if you have a Cauchy sequence here on the left-hand side, due to the isometry we proved here, you will have a Cauchy sequence also here. Yeah? So if you have here that we know that any H in the L2 space due to the density theorem is approximated by some sample function here. So this sample function is a Cauchy sequence. So this is a Cauchy sequence and is converging. And the limit is the Ito integral. But if we have understood this principle, we can extend it to Banach spaces, to the case where here the values of the integrand is in Banach. I will mention how. Okay, so proof of the second theorem. Given a sequence Hn such that Hn is converging to H in the L2 space. Then it is a Cauchy sequence, and Hn minus Hm in the norm of this L2 space is equal, we saw it, to the norm of the stochastic integral Hsn in the L minus H Sm in the L. Okay, and therefore it is clear that this limit exists. And is uniquely defined. And I call this limit obviously in the norm of the square integrable martingale. And the limit is what I call the Ito integral. It is simply the operator E, the closure of the operator E. It's simply the closed operator E. So now this operator is a continuous operator and is an isometry. So, okay, now suppose we have not anymore a Hilbert space. Then what we proved here doesn't work. We use the scalar product in this proof, yeah? But suppose we have a Banach space, and so I put here E. E is a Banach space, separable Banach. And now, suppose we would be able to prove that here an inequality holds. Yeah? If this is true, this inequality. If this is true, the whole theorem 2 is still valid. Because, again, if I have a Cauchy sequence here, I will have a Cauchy sequence here. And therefore, again, this operator here could be closed in the same way as, by the same arguments as before. Yeah? And this is a continuous operator, but this is not anymore an isometry. Yeah? So, moreover, E is not an isometry. It's only a continuous operator. Okay, so the question is, do I have such an inequality? Yeah? And moreover, I might have, for example, some constant in this inequality. I don't know whether I should take time to write it more ordered way. Maybe I should do it. Okay. So I write it more in a more ordered way, otherwise we become confused. Now I take here a separable Banach space. And then we assume now this, and then we will see when this assumption is satisfied. Yeah? We assume here that there exists a constant, K, and this constant might depend on the Levy process, L. Such that here I have that, well, this inequality holds with this constant here. I can put it maybe here. KL times this times KL times this, yeah? Is bigger than this. Then I have no problem in showing that this linear operator is closable. Because, as I said, it is clear that any Cauchy sequence here will still converge, because here I will have such inequality. Okay. 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 Under this assumption, this is true, because this inequality holds. So everything converging here is converging also here. Yeah? So the question is now, when does this inequality hold? So one sufficient condition is the following. Suppose that E is an, I will explain what it means, M-type 2 Banach space. I will define it. Then assumption holds. And therefore, Ito integral, here we have to assume in this case, this was theorem 2 prime, let's say, maybe 3. Assume assumption holds. Okay. Otherwise, it's not true. And this is the assumption. Okay. Then, if E is an M-type Banach space, then the assumption holds. And Ito integral is well defined. For all L2 functions. So for all, stochastic processes, H in L2 T, which are adapted. Okay? So what is a Banach space of M-type 2? Yeah? I will, M-type 2, in fact, type 2 Banach space. I will define it now. Sorry. So a Banach space the separable Banach space is of M-type 2. If for any discrete martingale with values in a Banach space E, if for any discrete martingale MK, with values in E, this Banach space E, such that E of the second moment is finite. It holds that the expectation of the martingale at time n, the second moment, is bounded by some constant k of the sum of mk minus mk minus 1, the second moment, for k equal to 0 to n minus 1, sorry, to 1. Okay. Suppose that your martingale is the sum of independent random variables, then this would mean that the sum of independent random variables has a variance which is bounded by the sum of the independent random variables. This is a type 2 Banach space. So a subspace of the M-type 2 space is the following. A separable Banach space is of type 2 if the following holds for any sequence xk of centered independent random variables with a finite second moment it holds that the expectation of the sum of this independent, the second moment of the sum of the independent random variables is less than the sum of the second moment. So as we know that this sum is a martingale, you see that the M-type 2 space is a smaller space than the type 2 space. Obviously, the question is, this definition is really very, well, strange. And one has no feeling for that. But in the 70s years, many people were fortunately working with that. So they had several results where they can tell us when a Banach space is of M-type 2. But however, you can imagine maybe why this M-type 2 condition is helping us. It is helping us because we wanted an inequality for the sample function. And the sample function were martingale, right? So they were martingales, and using this inequality here, which is true in any Banach space of M-type 2, we were able to show this inequality for the sample functions. Yeah, thank you. Okay. Yeah. Sorry. Okay, so as sample function are martingales, due to this inequality, we were able to show the inequality we needed in the assumption. Yeah? And due to this, we were then able to prove these theorems for M-type 2 Banach spaces. Now the question is, what are typical M2 Banach spaces? I mean, we use the definition of M-type 2, and we found our result, but the question is it useful or not? The answer is yes, because example of M-type 2 Banach spaces are, for example, the LP spaces on any measure space. with P bigger equal to and less than infinity, for example. These are all Banach spaces of M type 2. And other typical examples are all Banach spaces which satisfy the following property. The so-called uniformly smooth Banach space. I will say what it is. R of M type 2. These are the space which separable Banach spaces which satisfies the following property. There exists a constant K such that now the inequality is not given in terms of probability but in terms of geometry. The norm of x plus y square plus the norm of x minus y square is less than 2 norm of x square plus k norm of y square for each x y in E. So this is a characteristic given in terms of geometry. And if this is true, then again, Hoffmann-Jorgensen, I think, showed that then this inequality is true. Yeah? So there are useful Banach spaces where you can make Ito integral without being afraid. But not any Banach spaces Ito integral is well defined. There was a control example shown by Yor in the 75 paper, I think. So, okay, but now the question is, are these the only Banach spaces where Ito integral is well defined or not? It is a sufficient condition, the M type 2 condition. So, remark, the M type 2 condition is only a sufficient condition. But not necessary. Moreover, this M type 2 condition gives you a uniform constant in the inequality we had here. But we said that the constant for which we have an inequality here might depend on the Levy process. Yeah, this was our assumption. This here might depend. Wow. This constant might depend on the Levy process. If we have an M type 2 Banach space, this constant is uniform and not depending on the Levy process, because we use this inequality to show with the same K this inequality here. But you might have a Banach space which is not of M type 2, where for some Levy process, the Ito integral is well defined, and for other Levy process, it is not defined. A very stupid example is if you take a Poisson process, then you can show this to be true. Yeah? This is not so interesting example. But by the control example of Ruediger, there is some Banach space where for the Brownian motion this is not true. So M type 2 is only a sufficient condition, but not a necessary condition.
You're saying that there exists a Banach space where this inequality is not true for the Brownian motion defined with values on this Banach space.
Yeah.
But it's kind of default, or it's easy to hook up.
No, it's not easy to look, because I was looking at the proof again now. I wanted to find some more interesting control example for Levy jump, and it's not an easy proof. Yeah. I mean, I didn't spend too much time, but okay. But in any case, the following holds. Yeah?
There are no kind of characterization of the Banach spaces where these type of inequalities fail. These sufficient and necessary conditions to see what type of Banach space.
There is no Banach space where the inequality always fails, because you can always find some stupid Levy process which have maybe big jumps or a Poisson measure where it always holds. You find always some Levy process where the Ito integral is well defined. Whatever, but these are mostly those Levy processes where you don't need an Ito integral because they have finite variation. So these are not interesting examples.
The fractional Brownian motion can be put on these kind of things of M types.
I should think about that. But maybe one should also ask other authors who are interested in the subject, from Holland. I will tell you. Yeah, they are always interested in this kind of subjects. Okay, so let me just say one thing. In any case, it holds the following theorem. E is well defined as continuous operator in this way, if and only if there exists some constant KL such that assumption holds. So the assumption is not only a sufficient condition so that this operator is closable, but it is also a necessary condition. So in other words, E is closable as a continuous operator to a continuous operator I mean, on the sample function, it is always defined, right, as a Lebesgue-Stieltjes operator. But it is closable to a continuous operator on L2 if and only if the inequality in the assumption holds. So inequality in assumption holds. So this is the inequality. Sorry?
Greater than or equal to.
Yeah. Thank you. Yeah, sorry. Okay, this is some result we showed in 2009 in stochastic analysis and application. Moreover, we showed more. We showed that if the constant k, but maybe this is not so interesting for you now, if this constant k here is not depending on the Levy process, but it's uniform, yeah, then the Banach space has to be of type 2. Type 2 is bigger than M type 2. But for sure, if such a constant is not depending on L, like for example in the M type 2 case, then we know that for sure the Banach space has to be of type 2. So somehow type 2 conditions are related to the fact that the constant is uniform. But they are not necessary condition to the integral to exist. Yeah? Okay. So I did now, this part was not so planned in these details, but many people made question during the break yesterday, so I decided to put it. I hope it is somehow clean.
What happens in the warm between 1 and 2?
In what?
1 and 2 LP space between 1 and 2.
If I well remember, this inequality holds in the other way. It's the co-type 2 Banach space. So there I have problems. But it doesn't matter in the case you have a poor jump-Levy process. Because if you have a poor jump-Levy process, in fact, we could forget the whole theory we do usually. Because we could do all this in a, instead taking here MT2, we can take MT1 and L1 theory, and this always holds. So the Ito integral, if you do it for poor jump-Levy process in L1, holds on any Banach space always. But we do it usually in L2 because we have also the Brownian motion, yeah? And for this reason we do it in L2. But if you have only poor jump-Levy process, you don't need to do it in L2. So I didn't write the last statement, but I also don't know if it's interesting for everybody. Should I write it down, or just people who are interested are asking me? I don't know. So this is a little bit too detailed, maybe. I mean, we know that on Banach space of M type 2, inequality holds, and therefore Ito integral is well defined, but it's not a necessary condition, it's only sufficient. There are Banach spaces where inequality holds for some Levy processes also on other Banach spaces. And on Banach spaces of M type 2, the constant is uniform. Okay. Now, we were assuming the whole time that we were integrating with respect to Levy processes which have second finite moment, yeah? And I want to convince you that if we skip processes with finite variation, in this way we covered all the Levy processes we want to, yeah? We want to cover all Levy processes. So all Levy processes with have not finite variation have finite second moment. And for this reason, all centered Levy processes, obviously. And for this reason, what we did up to now was really okay. But I want to stress this property, and for this reason, I will now go back to analysis. So the Levy processes we considered were those centered Levy processes which are in MT2 of R. These were the one we were considering. And now I want to convince you that any centered Levy processes which has not bounded variation is inside here, so that we covered all possibilities which are interesting. Okay, so as later on I want also to present integration with respect to Poisson random measure, I need to give you some properties of Cadillac functions. So now I would speak about properties of Cadillac functions and Levy processes. Okay. So let me consider pure jump Cadillac functions. So let me define as a Cadillac, so a Cadillac function f from R to a Banach space E, which is constant outside the points of discontinuity. I call it is a pure jump Cadillac function. So for example, if E is equal R, the function will look like this. It is simply constant, then it has a discontinuity, then it's again constant, and so on. And it's always right continuous. Okay, we denote with delta F the jump. So delta F in T, it might be 0 if there is no jump, but otherwise it's exactly the jump. It's the value, the right value, minus the limes S, which goes to T in Fs. This is, for example, delta F at time T0. So now I want just to make some remark on what properties Cadillac functions have, which are pure jump Cadillac functions. So let F from R to E be a pure jump Cadillac function. Then the following properties hold. These are only remarks, in fact. So if I take the set, tau epsilon, tau, I write it bigger than epsilon t, of all those times in 0 to big T, such that the jump has a size bigger than epsilon for the time t. So then it is clear that this set here has only finitely many points. Because the function has some continuity properties. It is Cadillac. And if this would not be true, so exercise, show that if this is not true, it would explode. But this is not possible as F is Cadillac. It would explode in finite time. I cannot have infinitely many jumps bigger than given epsilon in a finite time. So obviously it follows from that if I consider all jumps, then these are numerable. F has at most numerable many jumps. So numerable many points of discontinuity. Okay, proof. Take epsilon equal to 1 to n for all n. And then you will see that the jumps are the union of the jumps here, and this can only be numerable. And therefore, if f is a pure jump Cadillac function, I can always write it in this way. It is the sum over those times where I have a discontinuity of the jump. It can be only look like this. It follows from 2. Yeah? Okay, and for I can decompose my function in 2 parts, and I know for sure that one part has finite variation. So I can decompose my function in those jumps which are bigger than a constant, for example, epsilon. So it is the sum of the jumps where the jumps are bigger than epsilon. Plus one part where the jumps are smaller than epsilon. So the norm of the jump times s here is smaller than epsilon. I am afraid you cannot read it, but okay. And this part here has bounded variation. Okay? So now we have, obviously, in this way, many informations about the path of the Levy process. So the variation of the part with big jumps for in any interval 0t this variation here is always finite. Yeah, finite for all t bigger than 0. Okay, now this is very interesting for our Levy processes because if we consider now a pure jump Levy process, then we know that at least if we look, if we decompose the path in this way, there will be one part which has finite variation. So it is not, it's a part where integration is very easy because we can do Lebesgue-Stieltjes. But in the case of Levy process, everything is a little bit sometimes more complicated. So, because then you have to pay attention that things are stochastically independent if you really want to decompose them. So this is only one part of the Levy-Ito decomposition theorem. The second part I will tell you later on, but it's not in the second part, we don't need it here. So given a centered Levy process, in fact, it's also true if it's not centered. Well, sorry, I don't need this. With values in A, separable Banach space in our case. Then we know that for each constant k, LT can be decomposed. Well, we know it path by path in the continuous path, and we said the Levy process with continuous path is a Brownian motion. In a pure jump Levy process, and here I consider all jumps bigger than k, and here I consider the pure jump Levy process with jumps less than k. So BT is the Brownian motion, and LT bigger than k is then simply the sum of the jumps of the Levy process such that the jumps have a norm which is bigger than k, and the other part is equal to the sum of the jumps where the jumps are less than k. But obviously, I am not finished here. I mean, for sure I convinced you that the path can be decomposed in this way, but this is not enough. I am speaking here that it can be decomposed as a process. And therefore, I need to also to state that these processes are mutually independent. So the difficulty of proving this theorem, I won't do it here because I need really much more. Especially, I need the second part of the theorem to prove the independence. Is not to prove the decomposition as a path in a continuous part and in this part here, but to prove that these are stochastically independent. Yeah? So I won't do the proof here. Yeah? Yeah, okay. No, because the drift I can, if you like, put it here. Okay, now it's better to put centered. You are right. Because otherwise there is plus AT. Yeah. Yeah, it was correct. What I wrote. Otherwise there is plus AT. Thank you. Yes, also the Levy process might have a drift, in fact. Okay, so the statement which I wrote there, I didn't finish to write it. The statement says also and BT, the pure jump process with jumps bigger than k, and the jump process with jumps less than k, as a process. As a process, in fact, are stochastically independent. Not only at time t. I will say what this means. Are stochastically independent. So what does it mean that two processes are stochastically independent? Two processes xt and yt on omega fp are stochastically independent if for any choice of t1, tn, the random vector xt1, xtn are stochastically independent. So in this sense, they are stochastically independent. Okay, so I won't prove now this theorem because I don't, the proof I looked at use the characteristic function. To introduce the characteristic function, I should say now much more about this. So it's not possible in that time. So, but it is in any standard book, in fact. For example, I can probably that it will be in Applebaum or whatever. Okay. Okay, but then we are very happy with that because, okay, I don't now speak about Brownian motion because I think you have discussed this very much. But now let us just look at Pur-Jump-centered Levy processes as good candidate to be define the noise. So we remark immediately then that Lt bigger than k plus Lt less equal k is a Pur-Jump Levy process. I mean, even if you separate them. Centered, sorry, Pur-Jump centered. But also that the variation of Lt bigger than k is finite for all t bigger than 0, p almost surely, because of the property we discussed here in number 4. So eventually, this part here is not interesting to define the noise, yeah, because you don't need to introduce Ito integral to define an integral with respect to this Levy process. So what about the other part? Can we there define the Ito integral? Well, we did it for real valued Levy processes, but anyway, this is now what I say is true on only separable Banach space. The answer is yes, because we want to define Ito integral, the second moment to be finite, and this is true for the other part. So you can prove the following, but this really I looked also, it's too long the proof, but it's done in Protter's book, that the moments of the Pur-Jump Levy process with jumps which are bounded by k are all finite for any n. We know this obviously also for the Brownian motion. So you see that if we have a Levy process, we have this part which might have moments which are not finite. So we might not be able to define Ito integral, but it doesn't matter because we can define a Lebesgue-Stieltjes integral. And then we have two other parts, and both have all moments finite. So the problem of defining Ito integral with respect to Lévy is not a problem, yeah? Okay. It's even in the first chapter, I think, very at the beginning of the book. I mean, Protter's book has also a very nice presentation of the Lévy-Ito decomposition theorem, yeah? I learned it first there. Okay, now I planned to go more deep in that because you will very often in some paper see that the non-Gaussian noise, when you don't have a Brownian motion, is not defined as an by the Ito integral I showed before, but it's usually defined, very often you will see that it's defined with respect to a compensated Poisson random measure, yeah? For example, you have here X. Oh my God. Something like that, something horrible like that. And I want to show you how you end up with this, yeah? In fact, I wanted to show you that this process here induces a random measure, which is this one, which expectation is given by this one. And finally, this integral, you can write it in this way, hs, x, and then this n. Okay, so don't worry if you don't understand now. So you can write it in this way here. So what people use as a noise usually is to generalize this. Instead of taking this, take any a, s, x here, or sigma. This is even more general than this. These are equal, and this is more general. So therefore, people usually use this because the possibility of considering noise is bigger, yeah? But now, with what I told you, you can first forget it. We do this, and this will be a particular case of what I will explain later on. Sigma is a progressively measurable function which depends on s, on x, because x is somehow the size of the jump. But I will explain this. Yeah, n is a Poisson random measure which counts the jumps of the Lévy process, and nu is the expectation. And this usually you can, and as it's a Lévy measure, in fact, you can write it like this. Okay, but I will explain this. But now, with the few knowledge I was able to introduce, only this, let us see what we can do with this. How we can define stochastic differential equation and solve them, yeah? And I will also speak about, because I know many people ask me, so I will also speak about stochastic partial differential equation. But today, first, let us start with simply think stochastic differential equation, yeah? So with few knowledge we have now, we can obviously do everything we know from the Brownian motion. I mean, the principles are the same, so I don't tell you nothing new. Okay. But let me recall for maybe also those who are not familiar with Brownian motion. Okay, so if you didn't understand what I say here, you can cancel it like I do now, completely from your mind. Okay, so first of all, what is the solution of some stochastic differential equation? Let us take them Banach valued, just not to do always the same thing which is well known. It doesn't make any difference because I have only need to have the noise to be defined and that's all. So I take M type 2 and I have it defined. Okay. And the rest is equal to what you know. So, but if you don't like it, you just think of R and that's it. I mean, given now LT, and in what I presented here, I presented always an integration where the noise is defined through is real valued, yeah? What is not real valued are the coefficient in the stochastic differential equation or the integrands when I integrate with respect to noise. Defined on some filtered space, omega f ft t. Filtered space, okay. Now I consider a stochastic differential equation of this kind. So here I have some drift, which depends on t, on the solution, and also on omega. Well, in probability, we don't use to write omega here. And then I have a noise drift, which also depends on t, xt, and omega, and my real valued Levy process. So this is my stochastic differential equation I consider here. And I take now the coefficient, depends also on omega, the drift coefficient and the noise coefficient, sigma. They have to be progressively measurable. I will say what it means, because we want to observe them on the same filtration. So A and sigma are in the space of progressively measurable functions. And these are the functions which are measurable with respect to the product sigma algebra at all. I take now time t, yeah? But also are adapted. I mean, it's not sufficient that they are measurable at the end time. They have also to be adapted at any time. So a function h is in this space of progressively measurable function. I just say prog. If, okay, h, which goes from r plus times e times omega to e, is such that it is measurable with respect to, so is, sorry, b r times be times ft measurable And it is adapted at any time. So h, t, x is ft adapted. For all x fixed. This has to be measurable on my filtration. So I assume this to be in this space of progressively measurable for all big T. Okay? Okay, now what is a strong solution of this stochastic differential equation? The process xt on the filtered space. It has obviously to be on the same space where we observe the noise. Also, the solution should be observed. So it's defined on the same. When I say it is on the filtered space, you remember I mean by that that it is adapted. Is a strong solution. Of the stochastic differential equation I have there. If P almost surely it holds for all T in, okay, is a strong solution in 0T, if you like. Yeah? If for all T in 0T, xt is equal to x0 plus the integral 0t of a of s xs in the s. This is obviously defined as a Lebesgue-Stieltjes integral plus the Ito integral sigma s xs in GLS. So now this is again somehow a stochastic process, and we had defined this, yeah? And we have defined it even for the case where sigma has values in a M-type 2 Banach space. But if you don't like it, just take Hilbert space, yeah? Okay, so the question now is when does a unique solution exist? I mean, there might be many theorems, and I present one of the easiest one, which tells you, and this is good for the first lesson we have, because the reasons are similar as in analysis, that if you have that the coefficients satisfy Lifschitz condition, then you have a unique solution. It is also true if it satisfies local Lifschitz condition. And you do it like you would do it in analysis, but in the right L2 spaces, that you prove it by making a contraction and showing that there is a unique fixed point if I defined this operator here, E of x to be this operator. And I can show, similar to what is done very often in analysis, that there is a contraction and a unique fixed point. But I think in 5 minutes I won't manage it, and to start a proof is not a good idea. So if you agree, I would stop here 5 minutes before. Okay.
You don't need any other condition on A?
On what? On? Growth condition and Lifschitz condition. For existence, it's also not. Yeah, yeah. Because with the fixed point procedure, I'm on, obviously, I have to do the fixed point procedure in the correct Banach space, which I have to introduce. But I introduce the correct Banach space and do on that correct Banach space show that if I call E of x what is on the right-hand side, I can't do a contraction, and that it has a unique fixed point, I mean.
if I want to do via Picard's iteration, I can consider only monotone operators A and C, right?
Yeah, I should think about it, but I imagine yes. I think what I propose is easier.
Yeah, it's easier.
Yeah.
Monotone is weaker than.
Yeah. Yeah. Okay, thank you.